Hello, good afternoon. My name is Roberto Vasquez, and I'm going to talk to you about how to build models of planetary nebulae in 3D from spectroscopic data. First, I would like to thank the ICPS organizing committee for inviting me to hold this workshop at this important event. We will start with some concepts about planetary nebulae and their importance in astrophysics. In 1764, the French astronomer Charles Messier first observed a planetary nebula. This is the object number 27 of his famous catalogue and now is known as the Dumble Nebula. This is an observation of the Dumble Nebula such as Messier would have seen it. And this is other one as we can see today using modern instrumentation. Charles Messier was a great astronomer. Throughout his life, he observed 44 comets, 13 of them discovered by himself, and 7 more in collaboration with other colleagues. Even more, Messier observed the return of the Halley's Comet in 1959. However, Messier was looking at blurry objects because they got in the way. All these objects, which were not stars or comets, were contemptuously called nebula. Now we know that what Messier put in his catalogue were not only nebulae, but also galaxies, stellar clusters, and in general everything that was not stars or comets. Our current concept of planetary nebulae is that they are expanding shells of ionized gas produced by the evolution of low and intermediate mass stars. In the slide, you can see examples of several planetary nebulae, some of them very well known. Years later, Carolina Herschel and her brother William made a catalog of more than 2,000 nebular objects, which 100 years later was improved by John Dreyer, increasing the number of objects to almost 8,000, including galaxies, nebulae, and star clusters. This is the famous New General Catalog, or NGC, if it sounds familiar to you about some objects. By the way, it was William Herschel who found the similarity of the planetary nebulae to the apparent greenish disk of the planet Uranus, discovered by himself, and for this reason he named them planetary nebulae. But he already knew that these objects were not related to the planets of the solar system. As a matter of fact, the 4.2-meter telescope of the Roque de los Muchachos Observatory and the Canary Islands was named in honor to William Herschel. And also was the infrared satellite that was scanning the sky between 2009 and 2013, the famous Herschel Space Observatory. We now know that planetary nebulae are always associated with an old or evolved star whose original mass was between 0.8 and 8 times the mass of the Sun, and which has surface temperatures between 25,000 and 300,000 Kelvin. On the other hand, the ionized gas shell emits visible light that corresponds to electronic transition mainly from hydrogen, helium, oxygen, nitrogen, neon, argon, and sulfur, among other elements. And it also emits in radio continuum, and some objects also emit in X rays. The temperature of the gas is between 5,000 and 20,000 Kelvin. Its electronic density between 1 and 100,000 particles per cubic centimeter, and its expansion speed is around 40 kilometers per second. One feature that distinguishes these objects is that the gas shell is expanding at a very high rate, but since they are so far away, they appear to us as static objects. The strange thing is that its rate of expansion is usually 2 to 4 times greater than the speed of sound. This is strange because if we have a thermal expanding gas, its expansion speed should correspond to the speed with which a mechanical information propagates. That is, the speed of sound. In 1978, Kwok, Burton, and Fitzgerald proposed a mechanism capable of explaining this phenomenon, the interacting stellar wind model. And in this picture is Professor Kwok currently at this time. Very happy. Let's try to understand it. First, we must know that stars are huge balls of gas in hydrostatic equilibrium whose brightness comes mainly from the temperature of their surface, which radiates the heat that comes from the nuclear fusion process. They are transforming hydrogen into helium and releasing energy. Stars like the Sun convert four hydrogen atoms into one helium, releasing energy in the process. Here we present the four equations of the stellar structure that account for the conservation of momentum or hydrostatic balance, the conservation of mass, the conservation of energy, and the temperature gradient. That is how the temperature varies from the center to the surface. With these four equations, we could already build a basic model of a star. Once the star consumes the hydrogen in its core, it undergoes changes in size, brightness, and temperature until it finds its equilibrium again by burning helium and converting it to carbon. Along the way, the outer layers of the star expand and the core contracts. At all times, the stellar wind is releasing material from the star, but much more easily in its later stages. Then, the core of the star promotes the formation of a much faster and less dense wind that reaches a slower wind, causing the interaction of both winds and producing a dense shell which is photoionized by ultraviolet radiation from the core. Thus, we end up with a hot core around a sphere of ionized gas. This is a planetary nebula, whose core is a hot and old star on its way to being a white dwarf. Planetary nebulae are excellent laboratories for many astrophysical processes, which has led astronomers to study them for different purposes. In our case, we will study their morphology and kinematics. But how do we know all this? Well, I think that using mirrors, prints, and selfies, or better, photos. For the astrophysicist, our laboratory is an observatory. And instead of doing experiments, we make observations. Sometimes looking at many similar cases is a very good substitute for performing many experiments. This is the building where the 2.1-meter telescope of the San Pedro Martir Observatory in Baja California, Mexico is located, very close to my place in Ensenada. Although other instruments and techniques are also used, the most common is to capture electromagnetic radiation. And of this, what we directly associate with astronomy is visible light. This is an optical telescope. This is the 2.1-meter telescope of the San Pedro Martir Observatory. And the last floor or the building that we saw in the other slide. One of the techniques we use in planetary nebulae is direct imaging, which consists of taking a picture of the nebula of our choice. Only the image itself can tell us much more about the nebula if we take monochromatic images, letting only one type of light through the detector. This is the planetary nebula KGPN8 that was discovered in San Pedro Martir in 1994. It was some master students. In the case of the stars, the color is given by the temperature. Stars emit light in all colors, but their surface temperature makes them appear in one predominant color that we know as the black body radiation. But in the case of the ionized gas, the process is a bit different. Matter is made of atoms, and atoms are made up of protons, neutrons, and electrons. One of the atomic models that helps us understand where colors come from the, is the Bohr model, in which atoms are represented as a planetary system. In the case of planetary nebula, the most important processes are photoionization, collision excitation, and recombination. In photoionization, the energy of an ultraviolet photon frees the electron from the atom. This is the ultraviolet photon and frees the atom. In the case of collisional excitation, it is a free electron that promotes the excitation of an electron to a higher level. This is the atom, and the other electron is placed to a higher level. However, whether a free electron is trapped again by an ion at a higher level or a bound electron has been raised by collisional excitation, there is a probability that the electron will spontaneously decay to a lower energy level, thus releasing the energy difference between the two levels as a photon. This is one photon of the continuum, and the other is equal to the difference of energy of uh, both levels. This process, called recombination, produces light of a very particular energy, which translates into a color. As this energy is so well defined and released many times, this emission is called spectral line, since a spectrum is the graph of intensity as a function of energy. A very important thing is that each different atom or ion emits its own lights, so we can know what chemical elements exist in a planetary nebula and where they are found. For example, these images were taken with a filter that only passes the hydrogen line H alpha, while these other images deal with emission of ionized nitrogen, the upper, and double ionized oxygen, the lower. Let's see this slowly. One way to obtain physical properties of nebula is spectroscopy, which consists of breaking down the light of nebula, analyzing their distribution, that is, their spectrum. For example, this is the Bowler-Chivens medium and low dispersion spectrograph installed in the 2.1-meter telescope. When we use this instrument, we pass light from a certain region of the nebula through a long slit. That light passes through a diffraction element, which can be a prism, but is usually a diffraction grating, in which produces a bidimensional spectrum where one axis is wavelength and the other axis is positioned along the slit. The real spectrum is not in colors, it's only for the picture. No? this is the resulting spectrum, but we learn more about the object if we add several rows that cross some region of interest, like adding these rows and extract the resulting spectrum to increase the signal to noise ratio. And we have this spectrum, this energy distribution. It's like a histogram of energy. With the extracted spectrum, the spectral lines from the certain atoms and ions can be identified. We can see oxygen, sulfur, nitrogen. Then we measure the fluxes, like in this table. And with the ratio of these fluxes, we determine physical properties such as temperature and electron density, the nature of the emission, or even chemical abundances. However, we're going to use data from the Manchester Shell spectrograph called MESCAL, which is a different, very high dispersion spectrograph, also on the 2.1 meter telescope in San Pedro Martir. Instead of analyzing all the colors, this instrument only concentrates on one or two spectral lines at a time and observe how the line deforms along the slit due to the Doppler effect. If you remember, the Doppler effect consists of detecting a high frequency in the wave emitted by an object when it approaches, and then detecting a lower frequency when it recedes. Applied to the sound, we hear a higher tone than the one that is emitted when we observe the object that is approaching, and a lower tone when it is already moving away, like this. That's because the waves appears to compress, like in the movie, in the direction of the motion and expand in the opposite direction. In the case of electromagnetic waves, that is light, the emission of a spectral line tends to the blue region when it approaches and to the red region when it moves away. This is what astronomers refer when we talk about blue shift or red shift. If it is familiar this for you, this word. The explanation of this phenomenon can be analyzed if we study the Doppler effect formula for a moving source. We see in the first expression here that the observer frequency depends on the speed of the wave and the speed of the source. And the second expression, we exchange the speed of the wave for the speed of light, c. In the third expression, we wrote the frequency as a function of the wavelength. In the fourth expression, we obtain the reciprocal in both sides of the equation. And from there, we do a bit of algebra to arrive to the final expression, where it is established that the change in wavelength with respect to the reference wavelength are proportional to the speed of the source. In fact, if we multiply the whole equation by the speed of light, we recover the speed at each point crossing the slit. And the units are kilometers per second. Okay? So instead of looking at the entire visible spectrum, we focus on a particular line and see how the Doppler effects warps it along the slit. With this knowledge, now we can interpret the kinematics and obtain the three-dimensional structure of the gas. You see in the picture, this is a spectral line, but it is like splitted to the red and to the blue. For example, here we make an artificial nebula. It is a perfect spherical shell to which an homologous velocity law that is velocity proportional to distance was imposed. In a spectrum with artificial slit was obtained. we see how each point in the slit splits into two speeds. One is the shell that approaches, and the other is the one that moves away, which is seen because the entire shell is semi-transparent. You see they all semi-hemispheres, the one in the other one. Of course, for non-spherical expansions, it is necessary to consider its projection, given that we will always see any three-dimensional structures projected in two dimensions on the plane of the sky. Sometimes it is possible to obtain the angle of inclination, for example, when we identify a ring, like in the picture, but it's not always the case. This is a real example of a spherical nebula that had four spectra taken as seen in the slide. And here you can see how the spectrum matches a spherical expansion of about 40 kilometers per second. Okay, it's, it's like you expect for a spherical shell. This is other one is NGC 6309, which is a very complex case. The data were finally interpreted as a system consisting of a ring and two pairs of bipolar outflows. You see all these complex spectra and the interpretation. This is an image, and the interpretation is this: two bipolar fluxes and one ring that match to the cases. These other are other cases, and we will work other objects, examples of models and nebula, and these are the articles we have done in different journals for professional astronomy. Many works from our students. Finally, I want to share with you that the open problems that planetary nebulae provide us with continue to be a highly topical field in modern astrophysics, and we hope that with modern instruments and techniques, we can move towards their solution. We will now proceed to solve a simple model of a planetary nebula. Okay? Um, ah, my final phrase. Remember, you and the planetary nebula have a cosmic connection because they are providing with elements that we use for life. Okay? Well,